Today we're starting Euclidean geometry, or I should say we're going to take what we've already done and we're going to build on it to create Euclidean geometry. That's really what we're going to do. A little bit of history about Euclid. Euclid was from Alexandria, and he wrote a book called The Elements. It was around 300 BC. It is a definitive treatment in 13 volumes of Greek plane and solid geometry and number theory. We could read it. Does that sound like fun? No? What a bum. Not so much. It would be hard to read it in Greek as well. All Greek to me, right? What he actually did is he built on the results of many mathematicians before him, but what he did that they didn't do is he was the first one to treat geometry axiomatically rather than practically. So he began with 5 axioms or postulates. His treatment was approved upon by a guy named Hilbert later on. Hilbert was a little bit more rigorous. And so when we talk about Euclidean geometry, we actually use Hilbert's 5 axioms or postulates because they're easier to work with. Okay, to avoid some of the writing that we could just have you copying down notes that I've already written on a screen and so forth, I handed you guys out some papers, right? Or a paper front and back. You can see Euclid's first 5 postulates, or his 5 postulates on the top, and then you can see Hilbert's axioms below. So what Hilbert does is he actually breaks them apart in ways that are easier for us to work with. We'll hit on some of these in our slides, not on everything. Obviously the incidence axioms we've already talked about. We spent a pretty decent amount of time talking about incidence geometry. But what we haven't done yet is we haven't actually talked about betweenness, and so that's kind of where we're headed next. So we had these incidence axioms with undefined terms, point, line, and incidence, axioms 1, 2, and 3, and we're going to need to continue to use those inside of Euclidean geometry. But now we have some betweenness axioms as well. So we have this additional undefined term called betweenness. Our notation for writing it is going to have some stars between things, so like A star, B star, C. And it means that B is between A and C. We have incidence axioms, or sorry, betweenness axioms written here. I'll read those in a moment, but one comment before we do. We sort of had a picture in our mind, like we did for points, lines, and incidence when we talk about betweenness. And our image that we have in our mind probably looks like something that we've called collinear, right? That somehow they lie in a line if they're talking about something being between them. So that's the interpretation that we've placed upon them in the Euclidean geometry we've done in the past. And it's not a bad interpretation, but it is just one interpretation. So let's go ahead and read through some of the betweenness axioms before I continue with the slides themselves, just so that we've sort of said them out loud and read through them together. So betweenness axiom number 1 says, if A star, B star, C, that means B is between A and C, then A, B, and C are 3 distinct points, all lying on the same line, right? That's that collinear we just talked about. And we could reverse the order, and we could write C star, B star, A equivalently. Now, if you'll remember, axioms are things that we don't prove. We just take them to be true, and we move forward, okay? The second one is axiom 2. Given any 2 distinct points B and D, there exist points A, C, and E lying on line BD, such that A star, B star, C, B star, C star, D, and B star, D star, E. Okay, so we've got points lying between and among all of the points that we talked about. Axiom V3. Axiom V3 says if A, B, and C are 3 distinct points lying on the same line, then one and only one of them is between the other 2. And if you think about the lines the way we talk about in Euclidean space, that makes sense. But if you think about what we talked about with lines being great circles on a sphere, that doesn't actually work, right? It wouldn't, because we've got this circular reasoning going on. So that sort of fails to be a model for Euclidean geometry for that reason already, at least. And then Axiom V4 says for every line L and for any 3 points A, B, and C not lying on L, this is talking about same-sidedness. If A and B are on the same side of L and B and C are on the same side of L, then A and C is on the same side of L. Can't speak very well. But if two of them are there and the third one is there, they're all three there. If A and B are on opposite sides and B and C are on opposite sides, then A and C are on the same side. And if you draw pictures to go along with these, you're going to say, well, yeah, we're just talking about the location as we sort of think about a line dividing a plane into two pieces, okay? All right. And I was realizing as I have this written, I don't know why it's written, but it's written in my notes and on here as well, that this should say Axiom B1, B2, B3, B4. So if you were jotting down notes, there's just one missing from that list. All right, so we're going to do some more definitions, some ideas inside of Euclidean geometry. We will come back to this in a moment. I don't know if it'll be, when it'll be today exactly, but we will come back to this worksheet, or not worksheet, but handout later on. So we're going to talk about a segment. We've been using segments all the time. In fact, a lot of times when you guys look at this AB segment, you think of it as being a line. You know it's not, but you think of it that way. But a segment AB is defined as the set of all points between A and B together with the end points A and B. It has a definite beginning, it has a definite end, and it contains everything that is between them. Along with that idea, we can extend that just a little bit. I've got one missing. My bad. I'll write it in. We want the definition of array. So the ray AB is defined as the set of all points on the segment AB together with all points C such that A star B star C. So it sort of feels like it's an extension of the segment. That's how it's being defined. Okay, so we've had lines for quite some time now. Now we have segments and we have rays. We didn't have those before. And we're going to talk about some propositions of what happens when we combine rays and segments together. And that's our first proposition. So proposition 3.1 says, for any 2 points A and B, the intersection of ray AB and BA is the segment AB, and the union of those two rays is the full line. As we work through some of these propositions, some of them are proved in your book, some of them I will prove in class, and some of them you will prove for homework, okay? So just because I'm not proving it doesn't mean that it couldn't be done. It just means it's going to be done in one of those other capacities. This one we're going to prove in class together, okay? And this proof is a little on the long side because there's two components to it. Okay, does everybody have it all written down at this point? I don't have enough space on this slide to prove it, so I'm going to switch to another slide. Are we good? Okay. All right, so we're going to start with the proof of number or letter I, number 1. And first, we will show that segment AB is contained inside of ray AB intersection with ray BA. Okay, that's what we're going to do first. Let me start down here. All right, so by definition of segment and ray, segment AB is contained in ray AB, and segment AB is contained in ray BA. That's part of the definition of segment and ray in particular. It's the one that I wrote in a minute ago. I promise I'll come back here in a second, but just to see as a reference. It's the set of all points on the segment together with additional stuff. Okay, so that's what we're using to start with. Thus, segment AB is certainly contained in their intersection because it's in each individual one. So it's contained in the intersection. I wrote that one wrong. There we go. Okay, so what we're going to do next is we're going to show the containment in the other order. All right, so one of the tricks to showing that things are equal is often to show that one of them is contained in this, the first one's contained in the second one, and the second one's contained inside the first one. The only way that happens is if they were equal to begin with. So that's what we're going to show second. Second or next, we will show ray AB intersect ray BA is contained inside of segment AB. All right, so we're going to let C be a point belonging to this intersection. So belonging to AB intersect BA. So what are we going to have to show about this point C? What would be useful to us? Yeah, it has to be on the segment AB itself, right? That's what has to be true. All right, very good. So then C, first, if C actually equals A or B, then C belongs to segment AB. It's kind of the trivial case, right? If it happens to be one of the endpoints we picked, then we're done. Otherwise, A, B, and C are collinear. And they're different. So there are 3 collinear points. They were collinear either way, but there are 3 collinear points. And by the definition of a ray, I'm sorry, I just read my writing wrong. There's no and right here. It's just by definition of ray. Okay, by definition of ray and segment, and axiom V1. That's why we know they're collinear. All right then, so by axiom V3, we have what Hannah mentioned. Exactly one of them is between something else. There's a betweenness argument going on. So exactly one of the relations holds. So what are these relations? Well, it could be that it's A star C star B, right? That's actually where we're going to end up, right? That's our anticipation. If we could get to that point that that's the one that's true, we'd be done. Or we could have A star B star C, right? B is actually between them. C comes after B. Or what's the third one? The A, yeah, I'm going to write it in the other order, but yeah, you've got it. So C star A star B. In other words, that the A is the in-between point of the three. Exactly. All right, so we've got to show why those other two, the second two, aren't going to work. So we will take the second one that we mentioned. Oops. If A star B star C holds, then what do you think happens in terms of the original rays we were talking about? What would be the problem? Where is C not?
Is it not in the intersection?
Okay, it's not in the intersection, but why is it not in the intersection? No, it wouldn't be an endpoint. So imagine, draw yourself a picture, what's going on. What we're saying is that we have, that's not a good spot. Well, it is, it's okay. Here's A star B star C. Can you draw in for me the rays? Where are our two rays that we're talking about? AB, which looks like this. And, there you go. And here's, oops. Undo, where's my undo? There it is. Here's ray BA. C is on ray AB, right, if we write it that direction, but it's not on ray BA. Right, this is the image that's going on as we're describing this. It's not on BA. And that's a contradiction, right? It was supposed to be on BA. So we can put our contradiction symbol. And we can do the same thing again. If which one did we do? We did A star B star C. So if we do C star A star B holds, what problem do we come up with then? Right, then C is not on AB. These are cases. These are the three cases, right? And we said that can't be true. So what does that mean? Thus, A star C star B holds, because there was only three choices, right? So C belongs to AB. And so what we really did, I'll write down one sort of concluding connection here. We said it, but I didn't ever write it. What we did is we actually showed that AB is contained in the intersection and that the intersection is contained in the segment AB. So since there's containment in both directions, what would have to be true? They are equal. And I said that, no, actually I apparently lied. We're not going to prove the second part of that. We're just going to prove the first part. It's very similar. The second one's the union. You would be using betweenness axioms in very much the same fashion. So we're just going to look at this one only today. Any questions on that one? Okay, next we're going to talk about opposite rays. If C star A star B, right, A is between C and B, then ray AC is said to be opposite to ray AB. And we can draw pictures to go along with these. If it's helpful to you, we can do that. So here are our three collinear points that are referenced. We're talking about ray AC, which is over here, and we're talking about ray AB, which is over here, and we would say that those are opposite rays. That's what you mean by you saying that. We're also going to talk about the sides of a particular line, especially because it's referenced in Axiom V4. So Axiom V4 talks about these sides of lines, and I read through it and had to sort of, you know, hem and haw a little bit about it, like, you know what this is talking about. So let's actually define what's going on inside of that. Let L be any line, and A and B any points that do not lie on L. If A equals B, or if segment AB contains no point lying on L, then we would say that A and B are on the same side of L. If the points are not equal, and the segment intersects line L, then we would say they are on opposite lines of L. So here's line L. And there's basically three scenarios that are described in this particular definition. One is the possibility that A and B are the same point. Well, if they're the same point, then they're clearly on the same side of L, because they are the same. The second scenario is that they're not the same, but if you were to connect them with a line segment, you would not cross L. So that would mean that A and B are on the same side of L. The third possibility is that when you connect them, you do cross L. And if you do cross L, then we would say that A and B are on opposite sides of L. And then that actually is enough to talk about our Axiom V4, I know we read it earlier, with some clearer vocabulary. It said for every line L and all 3 points not lying on L, if A and B are on the same side, and B and C are on the same side, so if A and B are on the same side, that means we can connect them with a line segment. B and C are on the same side, which means they can be connected with a line segment that does not intersect L. then we could also have a line segment between A and C, and it also would not intersect L. And on the flip side of that argument, if A and B are on opposite sides of L, which means they cross through L, and if B and C are on opposite sides of L, which means they also cross through L, then it must be the case that A and C are on the same side of L. Okay, did everybody get that all written down, drawn in, whatever you needed? Okay. Corollary to that axiom. If A and B are on opposite sides of L, and B and C are on the same side of L, then A and C are on opposite sides of L.
Is that what that word means?
Hmm?
What does that word mean?
What do you mean, what does it mean?
What does it mean?
You mean, would you like me to draw a picture?
The word.
The word corollary, is that the word you're asking me?
Yeah.
Corollary means something we're going to be able to prove. So the two words that we use kind of interchangeably as things that we don't prove are axioms and postulates. So anytime you see the word axiom or postulate, it means something that we take to be true and we don't ever prove it because it's not provable based on other facts. You have to start somewhere is the idea, right? Start with some sort of a foundation. Anything else that you see, corollary, theorem, postulate, lemma. Can anybody think of any others you've seen in any of your math classes? Those are the only four that are coming to my mind right now, are things we can prove. Usually corollaries and lemmas tend to be smaller facts, and postulates and, propositions and theorems tend to be bigger facts. Either they're bigger to prove, like they take more work, or they're a fact that's more significant. It just depends. So this is a corollary. It means it's a small fact. It shouldn't be that's terribly crazy to prove for it, and it's not. Visually, I think you guys already have a picture of this, but let me draw it just so that we can reference it as we're writing our proof. We have line L, and we're told that A and B are on opposite sides. And we're told that B and C are on the same side, like this. And we want to be able to say that, of course, A and C are on opposite sides. This is our image we have in mind. I'm going to move C just because it's taking up space I need. Okay, so we're going to get started with this one. Obviously, it's going to kind of draw back in on those definitions of what same side and opposite side mean, and quite possibly in our axiom, because we had same side, opposite side axiom information in B4. So we're going to take a look at this. So first we're going to start with our line L. So let L be any line. And A and B, as it's described, be on opposite sides of L. Is that how I started this? Oh, I'm sorry. I'm sorry. I was writing down something from another theorem. I'm sorry, just delete that. I just copied it. That's not what I meant to do. Okay, my bad. The proof. All right, so the proof is actually the contrapositive. It's even easier than what I was trying to make it. I was trying to make it more difficult. The contrapositive to axiom B4, part 2. And we will look back at that. I don't have it on the slide, but we will look back at that to verify that. All right, so Axiom V4, part 2 said if A and B are on opposite sides, B and C are on opposite sides, then A and C are on the same side. So if we were to take that and we were to do the contrapositive, if you remember, contrapositives mean that we start with the ending result and we make it the opposite. So the ending result says A and C are on the same side, which would mean we would start with A and C being on opposite sides, and we would turn everything backwards from where they are, okay? So we'd start on opposite sides, and we would end up with A and B on this, and I know my letters aren't matching up exactly right, but A and C would be on the same side, A and B would be on the same, B and C would be on the same side, excuse me, instead of the A and the C in their mentions. This is the contrapositive to that one. Yeah, and I missed a definition writing one down too. Okay. Definition, I sort of did everything but actually use this word a minute ago. I talked about the fact that a line sort of divides a plane into two pieces, right? This is our definition we're going to do right now. A side of L is referred to as a half plane bounded by L. Half plane. There's a example in one of the other classes I teach that has students try to take something that's infinite and break it apart. Break it apart into something that's finite and infinite, and then break it apart into two things that are infinite. So if you're imagining this, this is the breaking it apart into two things that are infinite, right? The plane is infinite as well. It's infinite in direction. So this is bounded. It has a line that bounds it, but it's still infinite in the other, if you will, two directions that we're talking about. Oh, I did have it on there. I totally lied to you. There it is. But you guys have it written down now. All right. Every line bounds exactly two half planes, which sort of makes sense. This is why when anybody starts talking about how many halves are there in a soccer game or how many halves are there in whatever, everybody looks at them like they're crazy. It's half, right? There's only two. The very words themselves define that in our minds that way. But every line bounds exactly two half planes, and the two half planes have no points in common. And we aren't proving this, but you can imagine how you would do that, right? You would assume, or at least one way is you could assume there's three of them, and you would run into a problem. You could talk about the fact that when you divide this into these two pieces, every point lies on one side or the other with the betweenness axioms in the same side, you know, the betweenness axiom number 4 that we talked about. Those kinds of arguments for proposition 3.2. Let's look at proposition 3.3.
If you have infinite planes, how do you have half of an infinite plane?
Imagine if you were to draw it out, and go back over here, not exactly a lot of space, but imagine if you were to draw out your plane, but you realized, of course, that it goes on in both directions, right? And I could draw the other two as well. And then you're drawing your line inside of here, and I don't care necessarily where you draw it, so I'm just going to draw it vertically. But it's still infinite up and down and left on the left-hand side, and it's infinite up and down and right on the right-hand side. But it does have a boundary. It's not infinite in all directions, it's just infinite in some directions. Does that make sense?
Yeah.
This is, no, I'm not going to say it that way. That doesn't make sense. Yeah, but this is the idea. It's still infinite. It's just broken apart into two pieces that are both infinite. Proposition 3.3 says the following. Given A star B star C, A star C star D, then B star C star D, and A star B star D. Just write it down. and then we'll do it with words. All right, so this is talking about things being between other things. So if B is between A and C C is between A and D, then C is also between B and D, and B is between A and D. And if you draw it in a picture, again, it helps to see what's going on. These are collinear descriptions, right? So if I have A and I have B and I have C, and they're collinear. That wasn't the right tool. That one is. And we are told that C is between A and D, then that means that I could, in some sense, extend the line that I just drew out here. It's an extension, and over here's D. And you can see as I did the extension that now B is in fact, or C is in fact between B and D, and B is in between A and D. And I'm not really extending something that doesn't exist, right? Those rays, those lines exist. We just didn't have them completely drawn. So as I'm drawing them, I'm not really creating something that wasn't there. Corollary. And if we were to prove this, maybe I should make that comment too. If we were to prove this, we would be using those betweenness axioms, right? We would be talking about rays and betweenness of those facts, and probably the proposition 3.1, I think it was, that we proved earlier about the segment and where things are on the rays. Corollary. If A is between C and B, and L is the line through A, B, and C, then for every point lying on L, that should say P lies, I'm pretty sure. Yeah. P lies either on ray AB or on the opposite ray AC. We're going to explore a little bit more with this idea later on. But what this is sort of saying is there's no gaps. There's no holes in what we're talking about. So if I draw these in again, C, A, and B, and L is the line that contains all three of them. And if you have a point on L, it must lie either on AB or on AC. There are no holes, there are no gaps. Pasch's theorem says if A, B, and C are distinct non-collinear points, so these are not collinear. Everything we've been doing today, it seems like it's been collinear. These are not collinear. And L is any line intersecting AB, segment AB, between A and B. Then L will also intersect either AC or BC. If C does not lie on L, then L does not intersect both AC and BC. So I'll try to draw, I don't have a lot of space on this slide, but I'll try to draw our picture above this. We have 3 points, and we have a segment AB. And there's a line L. And the line L crosses through AB. And it kind of has three possibilities. One possibility is that the line L crosses in such a way that it intersects C like this. A second possibility is that it crosses so that C is over there on the side with B. And a third is the possibility that C is over here on the side with A. All right? They talk about the one where it actually intersects C last, so let me just let C be on the same side as A. It's a similar argument if a C is on the same side as B. So clearly, if you connect A to C, L doesn't cross it. But if you connect B to C, it does, right? It definitely does. So it's going to intersect one of the two of them, has to. And if we had drawn it in such a way that it actually crossed through C, if the L actually intersected C, then it would actually intersect both AC and BC. I mean, kind of trivially, it wouldn't cross it in between, but it would cross it at its endpoint. And in no other way could it actually cross through both of them unless C is on the line L. And again, if we were proving this, this would be going back to those betweenness axiom number 4. All those propositions we talked to you about, same side and opposite sides. And that's actually where we're headed, is we're going to prove this one. So, y'all ready? Let's see. This is about as long as the last one that we did. And we talked about the fact that we have these points in this particular setup. So let's actually define that we have that. So A, B, C are not collinear. What else do we have? We have line L intersecting segment AB. Okay, I think those are our sort of conditions that we started with. So there's two things that are possible, and I kind of was drawing the picture as we talked about it, for C. C either lies on L or it doesn't. I mean, those are really the two possibilities. If it does, that is, if C lies on L, the theorem holds. It's the trivial case. By default, L intersects AC and BC because it intersects C. Okay? So that's the trivial case. We don't need to worry about that. So we're going to assume then that the opposite is true. So assume C does not lie on L. All right, so by definition, A and B lie on opposite sides of L. Right, that was our definition of opposite sides, is that they are able to be intersected, or that they do, their segment intersects this line that we're talking about. So they're on opposite sides of L. And then by axiom B4 and its corollary the corollary to B4, so the first corollary that we did. Did I label it with a number? It didn't have a number. It was this one right here. If you want to call it one, we can, but it was the corollary that came right after B4. So by Axiom V4 and its corollary, C is on the same side as something. So it's on the same side as A or B. Not both, but one or the other. So we're going to just let it be on one of them. Okay, so let C be on the side with A. Then it's on the opposite side of B. Opposite side that B is on. Thus, BC, that is the segment BC, intersects L by definition. That's what it means to be on the opposite sides. Intersects L by definition. Similarly, if C were on the side with B, or on the same side as B, hence the opposite side than A, then what could we say?
AC intersects L.
Right. AC intersects L by definition. Thus, AC or BC will intersect L. Okay, we're going to come across a few more propositions today, a few more definitions. I don't think we're proving anything else for today. Proposition 3.5. Given B between A and C, then the segment AC is the union of AB and BC, and B is the only point that's common to both segments. So proving this, we would probably want to talk about contradiction maybe, right? It says B is the only point in common. So clearly B is in common, the way that it's written. But we would want to show that it's the only point in common. We assume there's another point that does this. It would have to lie on both pieces, and we would run into a contradiction. In order to prove that in order to prove that B is the only point in common. To prove that the two sides are actually equal, we could do it a lot like what we did earlier on, where we would show that one is contained inside of the other one, right? 3.6, same condition at the beginning. B is between A and C. Then B is the only point common to rays BA and BC. And ray AB would equal ray AC. Now it's a little different than what we talked about before when we talked about opposite rays. So if we have A, B, and C, like such, and we drew our line between them, B, of course, is the only point on the two rays, BA and BC. But now we're actually talking about the rays AB, which would look like this, and AC, which would technically, if you sort of continued it, look like this, written on top of it. I'm sorry, I've drawn it sort of weird because I want to make sure you can see it. But those are the same ray. Not segment, of course, but they're the same ray. And again, we would look at containment, right? These are two equal things, so showing that one is equal to the other one by using a point in each one would be a good way to start that. So we've been working with rays now all day, and we're going to talk about how we join two rays together that are not opposite, and they create an angle. So an angle with a vertex A is a point together with two non-opposite rays, AB and AC, called the sides of the angle, emanating from A. So here's ray AB, and here's ray AC. Emanating from means just beginning at or starting from the same point A. They can't be opposite rays for the way that we're defining angle, okay? So we're not defining angle to include, so to speak, a straight angle. Notice that, because that would actually defeat this definition. It would make it not, it would contradict our definition. We have non-opposite rays. Now, with this picture, we can talk about other points that are not on the angle. What happened if the point is right here as opposed to right here? And we have different names for those two types of points. Was anybody still writing? I'm so sorry. Does anybody remember what we call those 2 points? Like what names we give them to differentiate their location with respect to our angle ABC? Or, sorry, BAC.
Interior.
Yeah, interior and exterior. So that's our next definition. Given our angle, CAB, the one I just drew on another page, if you take a point that's interior, it'll be on the same side of line AB as B, and also on the same side of line AB. I think that's typo. Yeah, the first one should say AC. Looks like that's not right. The same side of line AC as B, and then D is also on the same side of line AB as C. So if we were to draw this picture in, because this may feel like a little bit of an awkward way to describe this, but we've got our angle. And here's our point D. How did I draw it in? I could be on the bottom. So B, A, C. If I were to talk about extending or considering the line itself through AB, looks something like that. D is on the same side of the line as C is. And if I were to draw in line AC like that, D will be on the same side of that line as B is. In other words, it's the intersection of those two same sides. So these are my two sides, my two lines, and to be on the same side's intersection would mean that I have to be in here, which is exactly what we mean by interior. If a point's not inside, it's exterior. I thought I had written that one down, evidently not. Proposition 3.7 says, given an angle, CAB, and a point D lying on line BC, then D is interior to our angle if and only if D is between B and C. So in other words, another way to define this is that if we were looking at that angle that we had a moment ago, and we have C, I'm sorry, we'll keep my order the same, B, A, C, and D actually lies on line BC. So here's line BC, and it's actually along that line. That's actually what we know about it instead. That's only going to work if the D itself is actually on the segment as well. So if it's going to be along the line, it has to be along the segment, which would mean that it has to be between them. That's that betweenness axiom. Did everybody get that one written in? Proposition 3.8 says that if D is interior to angle CAB, then so is every other point on ray AD except A. No point on the opposite ray is interior. And if A is between C and E, then B is in the interior of angle DAE. The first two go hand in hand. So here's D in our interior. Then the ray AD, all the points on that ray except for A are also in the interior. And likewise, if I were to do the opposite ray, roughly speaking, it's over here, all of those points would be on the exterior. And then it's saying if we have a point A between C and E, in other words, if I were to extend this, then that point B will be in the interior of angle DAE. So let me draw in DAE since it's not drawn right now. It's in that yellow. Can you guys see that well enough? Try to make it a little bit thicker. That's better. B will be in the interior of that particular angle. All right, we're going to do one more today. It's a definition. Ray AD is between rays AC and AB. If, first of all, AB and AC are not opposite rays. And second of all, D is interior to the angle CAB, which was the picture I just had on the screen before. All right, so here's C, right, or angle CAB, and here is ray AD. We would say that ray AD is between AC and BC, those rays, if D is in the interior, which it is, and we actually had an angle to start with, right? AC and AB were not opposite. All right, we're going to pick up next time with what's called the crossbar theory. Before you put everything away, I want to make one more slide aware to you. We're halfway through Euclidean Geometry. We will finish it next time, which is fantastic. But I want you to have the homework for this section in case you would like to start working on it. It's not due until next Tuesday. It comes out of pages 119 to 129, so you're probably going to have to read and reference those as you do the problems on page 150. I'm going to warn you, these are multi-part problems, so it looks like I just gave you 2 problems, and that's not true. Okay? So please be aware, go back and look at them as soon as you have your book with your access to it to see what you're actually looking at, and they'll be due next week.